What's up? It's time to learn how these waves behave in the world around us. So we'll title this page, these two pages, Behavior of Waves. You can see we're going to define this idea of transmission, reflection, absorption, and refraction. And I'll also use refraction to discuss what happens inside of a prism and why a prism separates light. So I need you to stick with me throughout this video here as we discuss these different aspects, but many of them will probably come pretty easy to you with this nice gem at the end as we talk about the prism. All right, so let's start with our definition of transmission. All right, so transmission just means that the emission of waves, or a wave, we'll say the emission of waves through a medium. Okay, emission means that you are emitting something, you're releasing energy. So it's the release of energy in the form of a wave through a medium. A medium is anything that has substance. So that just means it could be like the air. It could mean emission of waves through water, through helium, if you've ever used a helium balloon to talk. And so the medium is something that is really, really important, and it affects the waves. And we'll look at that as we move through this. So sound. If we look at sound waves, sound travels through air very easily, obviously, because we all hear each other, and some other mediums. Like if you ever go underwater, yeah, you can emit sound, but you have to kind of scream in order to do that. So something that's interesting about sound is that it travels through air and some other mediums, but it does require a medium. So if you were to go out into outer space and scream for your life because you saw an alien, nobody would hear you. Well, there might not be anyone around, but the sound actually wouldn't be able to travel from you to the other person because there's none of those air molecules to bump into to get to that other person. Light is very different, or we could say electromagnetic radiation. It travels through air, obviously, because we can see on a day-to-day basis, and some other mediums, like it can travel through a window. It can also travel through other types of glass. It can travel through transparent and translucent materials. So it can travel through air and some other mediums, but it does actually not require a medium. It can travel through space, and luckily it can, because we get light energy and heat energy, actually light energy from the sun that travels to the earth, that our earth then traps the heat from the sun through our atmospheric layers. But the fact that it can travel through space is really awesome, because otherwise we wouldn't see anything here on earth. So that's the biggest difference, is that sound needs a medium, light does not need a medium to travel. Sound is a longitudinal wave, and light is a transverse wave. All right, so if we dig into how sound and light reflect differently. Reflection is a word that you probably are all aware of, but it's just that the energy of a wave bounces. We'll use this word, it bounces off of a medium. So if I've got this homie with a purple mohawk and they yell, Ricola, into the mountains, they might hear Ricola repeated back to them, because this is what we would call an echo. The energy of the wave bounces off of a medium that it cannot go through, so it bounces off of it and it returns, or it's reflected in a way that changes or moves the sound in a new direction. With light travels. If we had someone who's sitting here flexing in front of the mirror, the light bounces off the mirror and it comes back to the observer's face, so they can see how big their biceps are in the mirror and realize that they're just super ripped. They're swole. So both light and sound can reflect, but this is the difference between a mirror and an echo. It's just the type of wave that transfers, but both of them would be examples of a reflection of energy, of wave energy. What about absorption then? So absorption is the energy of a wave becomes engrossed, or we'll just use this word absorbed. I was trying to use a word that wasn't part of the definition or of the vocabulary term, so I didn't want to use absorbed, so engrossed would be kind of a word that we could use as well, because it kind of like takes the energy from the wave and absorbs it, it engrosses it into the medium. So if you think about like a sound recording studio, there's all this acoustic paneling along the side. This acoustic paneling is meant to actually absorb the noise, so it kind of vibrates and it takes the noise so that there is not a reflection of noise, because you don't want a reflection of noise in the microphone as you're trying to sing that love song to your favorite friend. But instead you want to be able to just have a nice recording session that doesn't have your echo in it. And so sound recording booths will use this acoustic foam to absorb the sound waves. Also some nice headphones too can absorb sound waves so that your whole family can't hear what you're listening to on your headphones, or if you're on an airplane listening to music, the people next to you don't have to listen. Now light is an interesting thing. If you have white light that is transferred through space, and if it hits something that is a black piece of felt, that black piece of felt is actually going to absorb the energy from the light, and it will actually get warm. So it will heat up. So the energy from the light will actually cause this thing to absorb that energy, and it will be transferred into thermal energy that we can measure, and we will see that there is a temperature change. And that's true of any color piece of fabric. It's going to absorb the light, and different colors will actually absorb it differently, and that is one of the experiments that you will do. So if we were to just kind of define this, we'd say that the black fabric absorbs light. And in contrast, actually, this is an example. If it was this white one, it's not a straight line, but we could draw it as a straight line because light kind of travels in a straight line because of the wave is such a tightly, it's such a tight oscillation that we can draw in a straight line. That it would actually reflect off of white. So that'd be a good example of absorption and reflection. Absorption and reflection. But here over in the sound booth, we would say that our acoustic foam absorbs sound. Okay, so you get that. So let's move on to refraction. This one's fun. Refraction means that the energy of a wave bends. That's right. It doesn't just bounce right back, but it's actually bent when it enters a medium that changes its speed. Fascinating. Okay, so we got, let's go back to where we were. Okay, so we've got our yodeler here, yodeling out into the air. And so we'll say they have a certain wavelength or a pitch. Well, if they were to yell through a helium medium, then their pitch would be changed. They would use the same effort, but their pitch would come out differently. So the helium molecule would be able to vibrate faster, which causes that sound to be a higher pitch. And if you go underwater and do that same yodel, then you will actually it might not even make it to the next person, because that wavelength, you need a lot more energy to make it through water. And so the sound waves are bent and they lose their energy. They're kind of almost like absorbed as it goes through the medium. So that's my best way to kind of describe refraction in terms of sound, but it's really a phenomenon of light. So if we think about light, if you were sitting in a boat and if you put your oar into the water, you'd be like, oh my goodness, what happened to my oar? When it's in the water, it looks like it's bent. But when it's out of the water, it's not bent. It's just a normal oar. So what the heck is happening? Well, when it enters the water changes the speed at which the light is going to return to your eye. And so it actually causes it to appear to be bent. And this same phenomenon can happen if you put a straw in a glass of water. You might see that part of the straw looks like it's disconnected and it's over to the left or the right, but in reality it's just the water that is bending that light, because the light can't travel at the same speed through the water as it can through the air. And this is why light ends up going through a prism, like the dark side of the moon record label here, or record image. And what's happening is that you have white light coming in. Now, something interesting that's different between color paint and color light is that if you put all the colors on a paint mat together, you end up with this nasty looking brownish gross color. But if you put all colors of the rainbow into light, it actually creates white light. I know, crazy. white light enters a prism. The prism has a medium that causes the light to change its speed. It has to slow down. Also, the angles in the prism cause this to the light to bend. So it bends and the speed changes. So we say the medium of the prism changes the speed of the light. When the speed of the light changes, each color, as we saw before, has a different wavelength. And so since the purple has a really close wavelength and the red has a longer wavelength, then the red ends up going at a different path than the purple does, and each color goes at its own path because it has its own wavelength. So when the white light gets split by the prism, it gets split because the medium causes the speed to change, the angle causes there to be a change or a bend in the light, and then the wavelength is what actually separates the light from each other. So what we can summarize here is that when the speed of the light changes, each color has a different wavelength and travel, or we'd say refract, at different speeds, which causes the colors to separate from one another. Now, what's so cool about this is you can use a prism then with any type of light and see what types of colors are in that white light, because it's not always all of the colors. Sometimes it might just be red, green, and blue, and that's the case for most LEDs. And you can say if you have a lot of red and a little bit of blue, you might end up with a purple. Or if you mix other colors and other combinations, you get different colors. So a lot of LEDs actually only have 3 colors in them, which you can discover by using a prism with an LED to see what colors are actually in that source of light. And we'll do that in class using some spectroscopy glasses, and we can look around the world around us, whether it's the sunlight or the light bulbs in our class for some LED light bulbs, and we can actually see what colors of light are in the white light that our eye is detecting. So it's pretty cool stuff, and this is also how a lot of astrophysics discoveries have been made, because we can learn a lot when we look at the universe and we can look at the different sources of light and how light is transported through the universe based on the original color of a material or the heat of a material. The amount of energy it has, we can use these prisms to kind of separate out the wavelengths to dissect the light a bit more. So refraction in light is pretty powerful stuff. And I hope you got your science notebook pages done. Hope I blew your mind a little bit, and continue on with the unit, and I will see you later. All right, see ya.